let's take a look at electrical circuits. And before we do that, we're going to remind ourselves about charge. Charge is a property of matter, kind of like mass. But unlike mass, charge can be both positive and negative. And remember, positive repels positive, negative repels negative. So like charges repel. Positive attracts negative, negative attracts positive. Opposite charges attract. There are particles called protons. Protons carry a positive charge. They carry the positive fundamental charge, which we call E, which is equal to 1.6 times 10 to the minus 19 coulombs. So a proton carries plus 1.6 times 10 to the minus 19 coulombs. They also have a pretty big mass for a subatomic particle. They have a mass of 1.673 times 10 to the minus 27 kilograms. Electrons carry a negative charge. They carry the negative fundamental charge, negative E, or negative 1.6 times 10 to the minus 19 coulombs. Electrons have a tiny little mass, tinier than the proton. Mass of an electron is 9.11 times 10 to the minus 31 kilograms. And then there are particles called neutrons. They carry no charge, and they have a mass of about 1.675 times 10 to the minus 27 kilograms, about as much as a proton. So let's think about these particles, and let's see what we could do to make them move through a path. Well, let's say we have a bunch of positive charges here, a bunch of negative charges here. We have a path right here. Well, if we did that, then positive charges would flow this way. Well, what if we put negative charges into this situation? Well, if I have positive charges here, negative charges here, put negative charges on this little path, the negative charges would flow this way, in the opposite direction. And if we had both, let's go ahead and draw the picture of both. Here's some positive charges, here's some negative charges, here's our path. Positive charges would move this way, negative charges would move this way. Now, in most of the applications that we look at, negative charges are going to be the ones that are actually moving. They are going to be what we call the charge carriers, the moving charges. And there's two reasons for this. Electrons have less mass than protons. So if we have a bunch of protons and a bunch of electrons, the electrons, because they have less mass, if we apply the same force to the protons and the electrons are going to have greater acceleration. Much greater, in fact, because the electrons have much less mass. The other reason is electrons are on the outside of atoms, and there are some materials where the electrons are relatively free to move around. They're called valence electrons, and if you study chemistry, you'll see those a lot. So electrons are going to be our charge carriers in almost all the situations we look at. Now, a material where these charge carriers, these electrons, are able to move around easily is called an electrical conductor. An example of that would be most metals like copper, aluminum, silver, gold. A material where the charge carriers, the electrons, are not able to move around easily is called an electrical insulator. An example of a material that's an electrical insulator is rubber, also plastic, wood, paper, air. And just as a side note, you can get charge to move through electrical insulators. It is possible for charge to move through electrical insulators, but it requires very large forces to do this. And when you apply those large forces and you get the charge to move through the material, sometimes you alter the material. So for example, lightning in air. You can get charge to move through air. That's what lightning is, or a spark is. But when you do that, it requires a large amount of force, and it's generally a pretty spectacular thing when it does happen. Okay, now imagine that we have a path for these charge carriers, these electrons, to move around. I'm going to draw an example right here. So instead of moving along a straight line, they're going to move through a loop. And right here, I'm going to draw just some kind of device. Don't worry about what it is right now, but it's some kind of device to push the electrons through this path. And this path is going to be made of an electrical conductor. So if we do that, then the electrons, these charge carriers, can flow this way. Now, we call this a circuit. A circuit is a path for charge carriers to flow through a loop. Now, the flow of the charge carriers, the flow of charge, is called a current. But there's a difficulty here. Current is defined to be the direction that positive charges would flow, which is opposite to the direction that electrons flow. So if the electrons are moving around this way, counterclockwise, then the current through this circuit is clockwise. Kind of strange. So let's give a formal definition of current. Current, which is represented with the letter capital I, is the rate at which charge flows past a point. And we have an expression for it. I is equal to delta Q over delta T, where delta Q is the charge that's moving past a point in a time delta T. And you can see the unit of current would be coulombs per second. A coulomb per second is known as an ampere. And if you remember back to our SI units, the ampere is one of the fundamental SI units. Now I want to remind you, current, what we call conventional current, is defined as the direction that a positive charge would flow through a circuit, which is opposite to the direction that negative charges actually flow through the circuit. All right. Now, I also want to go back to this little picture right here. We have this path that's made out of an electrical conductor where the charges can flow. We call that a wire. That is a wire, where the electrons here are able to flow freely through that path. That's called a wire. So back to this weird device that I mentioned, a device to push the electrons through the wire. What the heck is that? Well, often it's an electrical cell or electric cell, or a combination of electric cells called a battery. It could also be a generator or a power supply, or sometimes it's called a PD source. PD stands for potential difference. We'll talk about that later. But how the heck does it do it? How does it create this push? Well, in one view, it's creating an electric field in the wire. So if you imagine these electric charges, these electrons moving around the wire, there's an electric field inside the wire, and the electrons are moving in the opposite direction to the electric field. But somehow, another way to think about it, is somehow, either chemically, mechanically, electrically, somehow, it's creating a positive side and a negative side. So if we imagine a battery, like a familiar, say, C battery or D battery, one side has a little plus on it, one side has a little minus on it. And the idea there is that on the plus side, the charge, the electric charge, the electrons, have less electric potential energy. There's less potential energy on that side of the battery. And over here on the negative side, those electrons have more electric potential energy. Now again, we're not worrying about how the battery does it. We're not worrying about the chemistry that's going on or the mechanics that are going on inside of the battery. We just know, or I'm telling you, that the battery creates one side where those electrons have high electric potential energy, and on the other side, they have low electric potential energy. And if we have that, so let's draw the circuit here with the battery inside, and here's our wire. Okay, here's our little electrons, and here's the current. On this side, the electrons have low potential energy, and on this side of the battery, the electrons have high potential energy. Well, what would a mass do if it had high potential energy in one location and low potential energy in one location? Well, it would fall. If you imagine a mass with high potential energy, that means it's high up. And if it moves to a location with low potential energy, that means it fell. And it's analogous to what's going on with the electrons in this circuit. Over here, they have high potential energy. So you can kind of imagine, the analogy is, that the electrons are high up, kind of on a cliff here. And then as they move through the circuit, they fall down to a position where they have low potential energy. Now we're going to define potential difference now. Potential difference is represented with a capital V, and it turns out that potential difference is equal to the work per charge. And when I say work here in this equation, that's the work to move a charge Q from one location to another. And if we do that, then the potential difference here, that is the work per charge to move the charge from one location to another. The unit of potential difference, you can see, is the joule per coulomb, right? Work per charge, joule per coulomb. And a joule per coulomb is defined as a volt. So the unit of potential difference is a volt, which is represented with a V. So you have to be a little bit careful. We're going to have V's in the equation that represent the variable potential difference, and we're going to have V's that represent the unit volt. And when we have a potential difference, or PD, across a cell or a battery, we call that an EMF, or electromotive force. Now, going back to this circuit. So we have this circuit. The electrons are going to rush from the negative side of the battery to the positive side of the battery. They're going to rush through this electrical conductor, through this wire. And there's going to be a very high current. And so what? Right? That's neat. But why would we do this? What's the point? Well, we need another element in the circuit which is going to make the circuit useful, which is going to remove the energy that is in these electrons and do something with it. And that element is called a resistor. A resistor is an element in a circuit which removes energy from the electrons, and in doing so, it impedes the flow of the current. It opposes the flow of the current. So let's say we draw the circuit again. Here's our cell, and I'm going to add a resistor in there, and then here's our wires. Well, the electrons are going to flow from the negative side to the positive side, but as they do that, they're going to flow through this resistor. And the job of the resistor is that the electrons transfer energy to the resistor as they flow through it. Well, how much energy do they transfer? Well, that's given by our potential difference equation. If the potential difference here is the potential difference across both sides of the resistor, then the work here is the energy that is lost by an amount of charge as it flows through the resistor, and Q is the amount of charge that flowed through the resistor. Now we have another relationship here, and that is that the resistance of a resistor, capital R, is equal to the potential difference across the resistor divided by the current through the resistor. Now that R, the resistance, is a measure of how much the resistor resists the flow of current. It is measured in units of ohms, which is represented with a capital omega. And if we look at the units here, an ohm is equal to a volt per amp. Now the wires, meanwhile, have no resistance. Remember, the wires are made out of an electrical conductor. An electrical conductor allows charge carriers to move through it. So they have no resistance. They do not resist the flow of the current. So let's summarize. Here's our cell, and let's draw a wire, and let's put a resistor in our circuit like that. If we do that, our electrons are flowing in this direction, from this side of the battery to that side of the battery, which means that the current is then in the opposite direction. The potential difference across the ends of the cell is equal to the work that's done in moving a charge Q across either side of the cell, and that potential difference across a cell or a battery is called an EMF. Over here with the resistor, there's a potential difference across the resistor as well, and the potential difference across that resistor is equal to the work that's necessary to move a charge across the ends of the resistor divided by the amount of charge that we're moving. The resistance of the resistor is equal to the potential difference across the ends of the resistor divided by the current through the resistor. So the electrical cell or the battery here is adding energy to the electrons so that they travel around the circuit, and the resistor is removing energy from the electrons as they travel around the circuit, and the wires have essentially no effect on the energy of those electrons. Drawing this right here is a little bit messy, so we use symbols to draw the cell and the resistor, and the symbols look like this. Here is a cell. Long side is the positive side of the battery, and the short side is the negative side of the battery or cell. A wire is a simple line, and a resistor is represented like this.